Hi there, and welcome back to another tutorial. Today we're going to see how we can create custom nodes in Blueprint when the native nodes are not enough. Little disclaimer, while Blueprint nodes are interesting for that flexibility, they are usually slower in general than native nodes. So try to solve the problem first using native nodes. If you can't, you are at the right place. In this episode, we'll see a simple example that does a random point selection and output the selected points, discarded points, and an attribute set telling how many values are in each set. And in a follow-up video, we'll see a more complex one that do an operation in all points in multi-thread. Of course, the material will be on the Git repository, links will be in the description. Let's dive into it. I'll create a new graph and drag it into my scene. As usual, I sample the landscape, debug and inspect, and I will disable the density set on the surface sampler so all my points have a density of 1. If I want to take a random subset of this point cloud, I can use the select points node. To see the difference between the selected nodes and the others, I use the difference node. The source will be the surface sampler and the difference will be the selected nodes. Then I collapse the difference into points, and then I do a copy attribute to set the density to 0. So I create an attribute with a constant 0. My input source will be at last, and I will write into my density. And you can see that my density is 0 everywhere. Then I do a debug node to visualize it and drag my selected points and my discarded points. And you can see that I have black for 0 and white for 1. So I have a subset of my points, but there is a catch. The select points ratio is not a real ratio. It's a probability ratio, meaning that for enough points sampled with a ratio of 0.1, there is a high probability that it has selected 10% of the points. That's a problem when you have a very low number of points. But even at my scale, with a ratio of 0.5, with different seeds, I can have a very different number of points. The node is pretty fast, because we can compute the probability of each point to be chosen in parallel. But it induces this loss of control on the number of points we will have in the end. So the naive node is not enough for our purpose. So let's see how we can make a custom node that will do exactly what we want. Separate a point data in two with a precise ratio. In order to create a new element, you need to go into your content browser, then right-click on Blueprint class, and select a new PCG Blueprint Element. So I'll call it PCG Random Choice. You can find multiple overrideable functions that will be useful for customizing your node. But first, let's make sure we expose this node to the library so we can find it in our PCG graph. In the class default, you can find under Asset Info, Expose to Library. I can also add a category and description. So it will be under Custom Element, and description will be Choose Randomly Points. If I check it, save and compile, and go back to my PCG graph, I find it under my Custom Element with the right tooltip. The idea with this node is to split a set randomly using either a ratio between 0 and 1 or a fixed number. For example, if we have 10 points and a ratio of 0.2, it will choose 2 random points. Or we can ask for 3 points no matter what. Let's go back to our BP to add multiple variables for our node. So we'll have first fixed mode. If false, we'll compute the final number of points from the ratio, override from the fixed number. Ratio, a float between 0 and 1, and fixed number, an integer, if we want to extract a precise number of points. We mark them all visible, and by doing so, we will be able to change it from the outside, but will also be overridable directly by creating these pins automatically. I encourage you to check episode 5 to know a bit more on overrides if you are not familiar with. Now that our variables are set up, let's focus on the pins. By default, we have one in pin and one out pin, both of the type any. So we only want to support points in our case. So we go back to our BP, class default, and we uncheck the default in and out pin. For our input pin, we want an in pin with type points. And for the output, we want 3 pins. The first one will be chosen points of type points. The second will be discarded points of type points too. And finally, results. That will be an attribute set. It's not necessary per se for this example, but it is to showcase how to create attributes in blueprints. If I save and compile and go back to my graph, you can see that I have all my pins. Now that the I/O is set up, let's switch on the logic. We have different overridable functions that will be used by the PCG system. The most important ones are the execute functions. Execute with context will have the context as input, while in execute you can get the context with the get context node. You can use either of them, but it's probable that we'll keep only the execute one in the end. But for the video though, I will use the execute with context. So what is a context? Basically, it contains all the information useful for an operation. And it contains, for example, all the input and output data, also a pointer to the PCG component that is calling us, or the target actor. Or can also be used to generate randomness. It will pass along in BPs, but not used that much for simple cases. But if you do native nodes, it will be very important. We'll see it in another tutorial that focuses on C++ nodes. The first thing we want to do is gathering all the point data. The input pin contains a data collection. It's a list of all the data passed as input. If we break it, you can see it's an array of tag data. We want to get all the data that is passed on the in pin, so we will call get typed input by pin label. We will set the pin label to in, and the class we want is point data. In the return value, we have our data. So we will loop on all of them. Each element will be a point data, and we'll store the point data in a local variable in point data. That will be of type PCG Point Data object reference. And we will store our element inside this local variable. After that, we want to get the points. So we will create a copy of it. So we will create a new local variable in points of type PCG point, and we'll make it an array by right-clicking. To get the array of points as input, we use getPoints on our inPoint data, and we will set the array into our local variable. From there, we want to compute the number of elements to keep. So we will create a new local variable, num elements to keep, that will be an integer. We want to get the length of our array, and we want it to multiply by our ratio. To be safe, we're going to clamp our ratio between 0 and 1. Then we want to get an integer for it, so we're going to take the cell that will give us the next integer for a float value. So we will always have at least 1 point unless the ratio is 0. And then we want to do a select, and the option will be given by the fixed mode as a boolean. If the boolean is true, we use fixed number, and we also add a clamp to make sure that it is between 1 and the number of elements in our array. And it is if the value is true, and if the value is false, we use our ratio compute values. And we store it into our variable. When this is done, we can start doing our random. What is really important in PCG is that random needs to be deterministic. It means that for the same set of inputs, it needs to produce the same output. It's not a hard condition for PCG, but we encourage the user to respect this rule. Our random needs to be seeded. In PCG, the seed can come from 3 places: the component, the node settings, and a point. In our case, we will do a random combining the seed from the component and the seed from the settings. For that purpose, we can use getRandomStream directly from the context. It will return a random stream. For a random selection, we will shuffle the array. So we can call shuffle on our inPoints array. Then we can loop on all the points in inPoints. And if the array index is greater than the number of elements we want to keep, we want to do a select based on this boolean. We will store the points into arrays, but we need to create them. So we will create two new variables that will be for our chosen points and for our discarded points. If the boolean is true, it means that we will discard the point, so we will use discarded points array. And if it's false, we will use chosen point array. And then in the resulting array, we will add the point. With this, we have divided our points into arrays. We need to output some data now for PCG. One golden rule in PCG is that inputs are constant. That's very important and needs to be always respected. You always must create a new point data for your output if you modify your points. For that purpose, we will create 3 new variables. 2 of them will be PCG Point Data, and 1 will be an attribute set. So chosen point data and discarded point data as point data, and results as an attribute set. Now we can create our data. So at the end of the loop, we will construct a new class of type PCG Point Data. Then set it into our local variable, chosen point data. And then we will initialize our data using the in point data. This part is also very important because it propagates the target actor for this data, but also parent the metadata. Without this, any metadata stored on your input point data will be lost in your outputs, so don't forget it. When the data is initialized, we can set our points. So we'll get our chosen point data, then call the function setPoint, and we'll set the array of chosen points. And we will do the same for the discarded points. For our results attribute set, we're going to construct another class, and this one will be attribute set, but you will find under PCG param data, which is its deprecated name, but you will see attribute set, it is its display name. And we want to store it into our result data local variable. And then we want to add a new attribute. So we're going to get the metadata by doing mutable metadata. Very important. Never call mutable metadata on an input. Use constant metadata for that. Same rule. Inputs are constant, input metadata too. We want to create an attribute that will give the user the number of points we have chosen. So we'll use create integer 32 attribute to create an attribute of an integer, and we'll give it a name, chosen points num, and the default value will be the number of points that we want to keep. This is a bit technical, but for attribute set, it is important to add an entry in our metadata. For this metadata to at least have an entry. Entries are like the indexes for points. Without an entry, we will show no value, so make sure your metadata have one entry. We don't have to specify a value for this entry for our attribute, because if the entry is mapped to no value in an attribute, it will use the default value. In our case, the default value is the right one, but you can also explicitly set it with set integer 32 attribute by metadata key and use the key we just added. With the exact same attribute name and use the same value. As I said, metadata is a bit technical, but in 5.3, attribute sets are meant to have only a single entry. If you have multiple attributes, they all need to use the same entry key. It is assumed in a lot of places in native nodes that attribute sets have just a single entry. In 5.4, we'll support multi-entry attribute set, and this will allow us to have arrays. Now that all our PCG data are created and set up, we need to add them to the collection. So we will create an output collection as a PCG data collection. As we saw earlier, the PCG data collection is an array of tag data. So if I get my output collection and break it, you can see that it is an array of tag data. You can make a tag data and add it to the collection, but we introduced a simpler way to do it, directly from data collection with add to collection. You can set the point data, chosen point data, and also the pin. If you only have one default output pin, you don't have to specify it. It will make its way automatically there. But in our case, we have multiple output pins, so it is important to send the data to the right pin. So in this case, the chosen point data needs to go to the chosen point pin. And we will do the same for the other data. As for the tags, you can add tags to the data that can be used in graph afterwards. In our case, we don't have any tags, so we'll provide an empty array. We're almost done. Let's go back to the initialize for each loop, iterating on all the inputs. When the loop is completed, we just want to go to the output node, with the output being our output collection. Save and compile, and we're done. Let's test it out. I'll plug my data to our new node. And if I inspect the node and set a ratio of 0.1, I have data on all my pins. So I have 149 points as input, and I have 15 points as output chosen points, and the rest as discarded points. And in my results, I have one entry with the expected results. To visualize it, I'm going to copy what I did for the select point to set the density to 0. So I will copy it, then plug my discarded point into it, so all my points will have a density of 0. And I will add a debug node to visualize them. And so now you can see that I have like exactly 10% of chosen points, and the rest is all discarded. If I change the ratio to 0.2, I have twice as much. 0.5, I will have half of them. And if I switch to fixed mode and change the value to 5, I will have exactly 5 chosen points. Set it to 10, I will have exactly 10 points. And then I can also change the seed on the settings, and it will give me different results. Our logic also works for multi-inputs. Because we are iterating on all the inputs in the blueprint, we can plug multiple data into a node, and every data will be processed. So I will duplicate the surface sampler, change the seed, also add a translation on Z to just have them higher. And plug it in our node, and it will be picked up and computed automatically. And that's it for our first node in Blueprint. As an extra, let's see a few options we can play with to customize your node even more. You can change the default name of the node by overriding the function node title override. In my case, for example, if I write hello, my node will now be called hello by default. I will go quickly on that one, just that I will create a formatted string that will tell us if we are in fixed mode or in ratio mode, and will also set exactly the number for the ratio or for the fixed mode. If I go back to my graph, I have now the name updated. So if I change the value, I have the title that is changed. And if I change the fixed mode, I have the ratio now. We can also override the node color with node color override. If I want it to be yellow, there it is. Just change the color. Try to make sure to make it match the color with similar nodes. Otherwise, it can make it a bit complicated to understand what is going on. Something a bit more advanced, you can add the possibility to pre-configure node. The same way that we have add or multiply for the math node, we can do that with the blueprint nodes. In the blueprint class default, you can enable pre-configured settings. You can choose to only show the pre-configured one or also show the normal one. Then you can add multiple entries. They are known by their index. In my case, I'll add 1, index 0. and it will be random half split, and tooltip split randomly points into two sets of equal size. Then you need to override apply preconfigured settings. We break the input and plug the preconfigured index into a switch and set the fixed mode to false and the ratio to 0.5 on 0. And if I go back into my graph, I have random half split there. And if I click it, you can see it's automatically a ratio of 0.5. Before wrap up, let's talk performance. If I go in the profiling window, you can see that the select node is faster than the blueprint node. It's not a big difference, but let's increase the number of points. If I go back to my sofa sampler and change the extent from 100 to 10, and also change density, you can see that the blueprint node is 3.5 milliseconds, while the select points hasn't changed that much. So keep that in mind. Blueprints are very flexible, but it comes at the cost of performance. Of course, there are ways of optimizing it a little, and we'll see it in a follow-up video how to parallelize the operation on points, but it will never be as fast as native. Therefore, when you are satisfied with your BDP implementation, it can be worth to translate it into a native node in C++. I'll cover it in a future video, but as a teaser, here's the performance I have with a native version of the random choice. The blueprint version is more than 4 milliseconds, while the native is 76 microseconds. Pretty substantial, isn't it? I have the source code for this node in the GitHub too, but I cover it up in a future video. That's it for this one. You will be able to find the material for this episode and previous ones on the GitHub, and I hope it was useful. I see you next time. In the meantime, have fun with the plugin. Take care.